Hey class, in today's recitation we only made it through the first three problems, and 4 and 5 could be important for the exam that you're taking tomorrow. So I think I'm going to go through the first three problems kind of quickly, go over those again, and then we'll go over 4 and 5 as well. Um, so to quickly go through 1, 2, and 3. For 1, we're converting a regular expression into the equivalent NFA. And to do that, we need to start by looking at the base cases for regular expressions, which are the empty set epsilon or single character. So we'll go ahead and grab the first single character here, and we will make that regular expression into its equivalent NFA. So B is itself a regular expression because R equals A is one of the rules for regular expressions by definition. So we'll start out by creating the NFA that recognizes B. And then we need to also create the NFA that recognizes the regular expression A, or convert the regular expression A into an NFA. So again, we'll do the same thing here. Create the simple NFA that just recognizes the character A. And now we have two NFAs, and we need to union the two NFAs together. So we can do that, of course, by creating a new start state and adding epsilon transitions from the new start state to the old start states. So this completes the B union A. And next we have the Kleene star, the star that we need to apply to this entire NFA that we've created. And in order to create star, we first create a new start state. And we epsilon transition from the new start state to the old start state. We also will create epsilon transitions from all of the final states of the NFA to the new start state. And we need to make that new start state a final state as well. So next we have this NFA unioned with the concatenation of the regular expressions A, B, and A star. Now note that this isn't the union of the existing NFA with just A, because the order of precedence for regular languages goes from 1 star, so star always goes first, 2 is going to be concatenation, and 3 is union. So in this case, both the star for A star as well as the concatenation of A, B, and A come before this union. So we will again need to first create the NFAs for A, the character A, an NFA that recognizes the character B, and an NFA that recognizes the character A. So we can do that here. And these will be the same as the ones that we created before. So now we have separate NFAs that recognize A, one that recognizes B, and another one that recognizes A. However, before we concatenate them, again we have to look at the order of precedence, and we see that the Kleene star comes first, which means that before we can concatenate B with A star, we first have to actually create A star. So we need to convert the NFA of A into the NFA for A star. We do that by creating a new start state and epsilon transitioning from the new start state to the old start state. We need to make the new start state a final state, and we need to epsilon transition from all of the existing previous final states to the new one. So this gives us a star, and now we need to concatenate the NFAs for A and B. To concatenate an NFA, you do so by creating an epsilon transition from the start state, or from the final state of the first NFA to the start state of the second one. So we'll do that here, and then you need to remove the final state, make the final state of the first NFA into just a regular non-final state. And now we'll do the same thing for the concatenation of this NFA of AB with the NFA of A star. So again, we will create an epsilon transition from the final state of the first NFA to the start state of the other, and we will remove the final state of the first NFA from the set of final states. Now we've completed the B union A star and the AB A star. Next on the list is to union those two NFAs together. So we have these two separate NFAs, and to union two NFAs, you create a new start state and add epsilon transitions from the new start state to the two previous start states of the previous NFAs, giving you a new single NFA that recognizes the union of the two. Finally, we have the star outside of this entire NFA here. So we have created this whole NFA, and now we need to convert it into the star of that NFA. You do that by creating, again, a new start state. You add an epsilon transition from the new start state to the old one. You add epsilon transitions from all of the final states in the previous NFA to the new start state, and we have a few of those here. I think I'm just going to join these all together. So here there's a bunch of transitions coming out of here, and they're all epsilon. And there's another final state here, and another final state here that'll both be epsilon transitions to the new start state. And the last thing that we need to do is make the new start state a final state, which will give us the NFA equivalent of the initial regular expression. Now, what is the purpose of doing this? Why are we creating a regular expression to the equivalent NFA? Well, what we're trying to do is show that regular expressions are equivalent to NFAs. And in order to do that, we need to not only show that you can convert a regular expression to an NFA, but that you can also convert an NFA into a regular expression. So that's what's next on the list. We are given an NFA, and we need to find the equivalent regular expression for that. The first thing that we need to do is convert this NFA into a generalized NFA, which instead of having characters on the transitions, will have regular expressions. So that's the first thing that we need to do is change the transitions from characters like, let's see, A is an element of sigma star into regular expressions. And the other thing that we'll need to do is in order a GNFA requires that you have a start state that has no incoming transitions and a final state that has no outgoing transitions. So in order to do that, let's first add that here. You know what? My handwriting's so bad with this that it's not worth it. So, well, we won't be writing the rules down. Okay, so let's start rewriting this. We know that we need to have a start state with no incoming transitions, but we can see that right now Q0 is our start state, and it does have this incoming transition A. But that doesn't matter. Anytime that we see an NFA, the first thing that we're going to do is create a brand new start state. We'll call that QS, and epsilon transition over to the old start state, Q0. Now, I've added in the rest of the existing states as well as their transitions, but without the labels. The next thing that we need to do in order to make this NFA a GNFA is to make only a single final state, or have a final state that has no outgoing edges. So to do that, we can simply create a new final state, which we can call Q sub F, and add epsilon transitions from the previous final states to the new one, and then remove the previous final states from these sets of final states. Now, for the transitions, we need to change the transitions from these input characters into regular expressions. Now, single characters are regular expressions, so we can go ahead and put in anything that's a single character, like this B, this A, and this B. But now we have this A comma B here, which is really syntactic sugar for having two transitions from Q2 to Q1, one that has A and another that has B, and we just kind of put them together. Well, in GNFAs, when instead of having multiple transitions, if you're about to make a second transition between some state and another state, instead you'll union whatever transition was there with the new transition that you're trying to add. So let's say we have the transition from Q2 to Q1 with A, and now we're trying to add the transition from Q2 to Q1 with B. Well, if we already have A here, we'll then union that with B. So visually, the only difference is that here we have the union symbol and here we have the comma, but there's a few things that actually go on in order for us to do that. Now, it's important to note that as we convert this GNFA into the equivalent regular expression, that the order that we remove the states from the GNFA will affect the regular expression that we get in the end. However, the different regular expressions that you get from removing these states in different orders will be equivalent. So it doesn't matter what order you remove those states. The first state that we remove from this NFA is going to be Q1. So I've gone ahead and drawn in all the states that aren't Q1, as well as all the transitions that don't go to or from Q1. Now we need to figure out what the new transitions will be without Q1 being there. The first thing to look at is how many transitions are we going to have to make? Well, we can look at the total number of transitions coming into Q1, which is 2, and the total number of transitions going out of Q1, which is also 2. And we can multiply those numbers together, which of course gives us 4, and 4 is the total number of transitions that we should be drawing here when we rip out Q1. You could also note that from Q1 to Q0, Q0 has one incoming connection from Q1, and Q1 has two total incoming transitions, which means that we know the total number of transitions that we'll be drawing into Q0 is 2. Similarly, the total number of transitions that we'll be drawing into QF will also be 2. Let's start by looking at the transition from Q0 to Q1, which is B. From Q0 to Q1, and then we can go from Q0 to Q1, and then we can go from Q1 back to Q0. So when we rip this out, we will have a new transition on Q0 with the regular expression of B concatenated with A. And because Q0 was the source state and Q0 was also the destination state coming out of Q1, it'll be a self loop from Q0 to Q0. Next, we can see that following that same initial transition of B from Q0 to Q1, we can then go from Q1 to QF with an epsilon transition, or an epsilon regular expression. So we'll concatenate B with epsilon, which is just B. And that will be the transition from Q0 to QF. Now we've drawn two transitions. We know from the math we did at the start that we have two more to go. So we also have the incoming transition to Q1 of A union B. So we'll say A union B concatenated with one of the transitions leaving Q1. So A union B concatenated with A will go from Q2 to Q0. And notice the parentheses that I'm drawing around the A union B. You need that because of the order of precedence. Otherwise, it would try to concatenate B and A before doing the union, which would be incorrect. For our final transition, we also have that same incoming edge, A union B, and the outgoing transition from Q1 to QF, which is epsilon. So we'll go from the source node of Q2 to the destination node, or destination state QF. And we'll concatenate the edges, concatenate the regular expressions. So here we have A union B. A union B concatenated with epsilon is just epsilon. And it looks like I forgot to draw QF as a final state. So we'll go ahead and add that. And next up, we'll rip out, let's say, Q2. So I'm going to draw in all of the states and the transitions that don't involve Q2. And we can see from the previous GNFA that Q2 had a total of 1 transitions coming into it and 2 transitions leaving it. Note that the self loops are not counted as incoming or outgoing transitions. So let's start by going from this Q0 to Q2 on regular expression A. From there, we can go from Q2 back to Q0. So we'll concatenate A with B star for this self loop on B, and that A B star will be concatenated with the A union B A here. And that's going to bring us from state Q0 back to state Q0. Now you might ask, well, wait, we already have a transition from Q0 to Q0, so what do we do? And in that case where you're adding a new regular expression to an existing transition, you'll simply union the existing regular expression with the new one. So we already have BA. Now we're going to be unioning BA with A, B star, A union B, A. Now we also have the transition that goes from, again, Q0 to Q2, but now out from Q2 to QF. So from the initial state Q0, or the initial state Q0 to the final state QF, we again already have a transition drawn there. So we're going to union our new regular expression with the existing regular expression that was on that transition. So I will draw the B here, and we're going to union that with A from this guy, B star from the self loop on B, and the A union B to QF. The last state available to rip out is Q0, so I'm going to go ahead and draw in the other states, QS and QF. And now when we rip out Q2, we can see that when we rip out Q0, we can see that Q0 has one incoming transition and one outgoing transition. So 1 times 1 is 1, and that means we'll have a total of 1 transition, which is exactly what we're trying to get to here. And that transition will be the concatenation of this epsilon with this regular expression, which is on a loop. It's the self loop, so that's going to be the regular expression starred. And that will be concatenated with the regular expression from the transition from Q0 to QF. And since these are now getting long, because these are all regular expressions, I can say that this monstrosity on the top equals R1, and I can say this monstrosity on the bottom equals R2. And now I can perform these concatenations using just R1 and R2, knowing that it works because they're regular expressions. So we have epsilon concatenated with R1 star, which is just R1 star, concatenated with B union A B star, A union B. Or actually, I didn't have to write that whole thing out. This is the reason that we just set them equal to regular expressions R1 and R2. Instead of writing that, I can simply say R1 star concatenated with R2. Now, the answer for the regular expression is not this entire thing, but rather the regular expression that we have on the single transition left of the GNFA. So the regular expression, the answer to this is R1 star R2. Now, I'm not going to write out the entire proof for the pumping lemma of regular expressions, but I did write on the side here kind of the 3 requirements for a string x, y, z is an element in L, assuming that L is regular. Now we have the problem, prove that the language L equals a to the n, b to the m, c to the L, such that n equals m plus L, or m equals n plus L. Now the first thing that we need to do to prove that this language is not regular is to find a string that doesn't meet these requirements, and we're going to do this by assuming that this language is regular, and then coming to a contradiction. So we'll start out by saying that we assume L is regular, and if L is regular, then there exists a pumping constant P for the language L. Now we need to choose a string in the language that the string has to be in the language, and the string has to be at least length P. And let's look at how we can do this. We have a to the n, b to the m, c to the l, such that n equals m plus l, or m equals n plus l. So let's say that we made m equal to p and l equal to p, which would mean that a string in the language would have an n equal to 2p. With that, we can write out the string that we're selecting as a to the 2p. So w, let's say, let w equal a to the 2p, b to the p, c to the p. And we can note here that w is in fact an element of an L, and clearly the string is of at least p because we have 2 PAs at the start. Now we need to find the split XYZ of this string that will allow us to pump the string. And we'll start by looking over here and notice that rule 2 states that the length of x and y is going to be less than or equal to p, which is going to limit the possible ways that this string can be split up. And in fact, because we already have 2 PAs, it means that both x and y will only contain a's. So we can write that x is going to equal some amount of a's, so a alpha, and y is going to equal some amount of a's, we'll say beta a's, and z is going to equal a to the 2p minus alpha minus beta, b to the p, c to the p. It's also worth noting here that the value of beta equals the length of y. So we can write off to the side over here that the length of y equals beta. Next, we'll choose a value of I such that x, y to the I, z is not going to be an element in the language, or that's at least our goal. And I can be any value greater than or equal to 0. Well, let's say that we picked I to be 0. That means that we are going to have y equals a to the beta times I, which is 0. And our string will look something like this. We have a to the alpha, a to the beta times 0, and then a to the 2p minus alpha minus beta, b to the p, c to the p. Now we'll want to simplify this. So here we have a to the alpha, and here we have a to the negative alpha. So those two are going to cancel. Here we have b times 0, which means that this a is going to disappear. And it's going to leave us with the string a to the 2p minus beta, b to the p, c to the p. And if this is the string that we get when we pump I down to 0, then this is now a string, and it has to be in the language, right? Well, what does the language say about these strings? It says that you'll have a to the n, b to the m, c to the l, which means that each of these things that are written like powers up here, the superscripts on these characters, are equal. This one is equal to n, and this one is equal to m, and this one is equal to l. So we see from the initial rule that n equals m plus l. So we have 2p minus beta equals b to the p, c to the p. Well, or I'm sorry, not b to the p, c to the p. It's 2p minus beta equals p plus p for the m plus l. And p plus p is, of course, 2p. And if we subtract 2p from the left side and the right, and from the left side and the right side, then we end up here with beta equals 0. So in order for this string to be in the language, beta has to equal 0. And beta, as we wrote over here, is equal to the length of y. However, we can see from Rule 3 of the pumping lemma of regular expressions that the length of y must be greater than or equal to 1. So the lemma is telling us that the string is in the language. However, the language itself is telling us that the string can't be in the language, which is a contradiction. So we can assert that we have made an assumption in this proof that is false. And the only assumption that we've made is that L is regular. So proof by contradiction then states that L is not regular. Next, we'll move on to number 4. Number 4 is a regular grammar, and regular grammars are of the form V sigma R and S, where V is a set of variables, sigma is a set of terminals, R are the rules of the regular grammar, and S is the start state. Now, the rules are what we've been provided with here. The variables we can see on the left-hand side, and the terminals are going to be the 0 and 1s that we see within the rules. So for rule T, we have T goes to 1A. So we will go from T to the state A with input of 1. The second rule for T is T to 0T. So we will go from T back to T, input 0. Finally, we have the rules for A. So A goes to 1s, so we'll draw a transition from A to S on input 1. A can go to 1a, so we will transition from A back to A with input 1. And A can go to 0t, so we'll transition from A to T with transition 0. And we are left with the NFA equivalent of the regular grammar. Now, just like going from a DFA to an NFA, the purpose of going from an NFA to a regular grammar is to start trying to prove that regular grammars and NFAs are equivalent. But in order to do that, you have to show that you can convert both from an NFA to a regular grammar and from a regular grammar to an NFA. So we've done the latter. Let's go ahead and do the former. We're provided with an NFA and asked to create the equivalent regular grammar for it. So we already have up here what a regular grammar formally is defined as. So we can just start building that by looking at our NFA. To start, we need the variables v. So we'll say here that v equals the set q0, q1, q2, q3, and q4. You create a variable for each state in the NFA. Next, we have sigma. And sigma is going to equal the set of terminals, which we can find by looking at the transitions in the NFA. It'll be the values of the transitions minus the set containing epsilon. So here we have the set 0, 1 for our terminals. We also need to identify a starting variable. So S clearly is labeled as Q0 in the NFA. And finally, we need to come up with the rules. So for each of the variables, we are going to create a set of rules for them. So I will go ahead and just draw out ahead of time Q0, Q1, Q2, Q3, and Q4. Starting with Q0, we are going to create a rule for each transition leaving the state Q0 in our NFA. So we can see that we go from Q0 to Q2 with symbol 1, which means we are going to create a rule that goes from Q0 to 1, Q2. We have another transition leaving Q0 to Q3, so we will have a rule 0, Q3. That is the last transition leaving state Q0, which means we are done creating the rules for our variable Q0. Moving on to Q1, we can see that Q1 has a self loop in the NFA, so it goes from Q1 back to Q1 on input 0. So we'll create a rule that goes from Q1, generates the character 0, and then add the variable Q1. Q1 also has a transition to Q3 on input 1, so we're going to create another rule that says that with variable Q1 it's going to generate a 1 and the variable Q3. Moving on to Q2, Q2 has an epsilon transition to Q0. So we are simply going to create the rule that goes to the variable q0, and it has a transition to q4 on input 0 and on input 1. But note that in regular grammars, you can only generate one terminal per rule, which means we're going to need to create separate rules for 0 and 1. So we'll have 0 q4, and we will have 1 q4. Moving on to q3. q3 only has a single transition to itself on input 1, so we will create a rule that generates the character 1 and transitions to q3. Also, q3 is a final state, which means that it can stop generating characters for the string and then produce the string for the language. In order for that to happen, we can simply add an epsilon rule, which will drop the rest of the string. Finally, we have q4. q4 has two transitions leaving it, so we have q4 to q1 on input 0, so we'll create a rule that generates the character 0 and then has the variable q1. And the other rule from q4 to, or the other transition from state q4 to state q2 on transition input 1. So we are going to generate the string 1 and then put in the variable q2. So we now have a rule for every transition in the previous NFA, and we have completed the definition of a regular grammar. That is, again, V, sigma, R, and S, where R is the set of these rules.